In this video, we're going to talk about finding probabilities for a binomial random variable. So in the last video, we talked about binomial distributions and binomial random variables. We said that x is a binomial random variable if x is the number of successes in n trials, where the probability of success in one trial is p, and certain other conditions were met, that the trials were independent, that the probability of success was always p, there's a fixed number of trials, then in that case, this is a binomial distribution. And we found the probability that there were k successes in n trials. The probability that x is equal to k is given by this formula, and we can either read that as n choose k times the probability of success to the kth power times the probability of failure, which is 1 minus p to the n minus kth power, or we can read it in the following way: n factorial divided by n minus k factorial times k factorial times the probability of success to the kth power times the probability of failure to the n minus kth power. So let's look at a couple examples. For the first one, suppose that 60% of registered voters in Berkshire County are Democrats. If 12 voters are randomly selected, find the probability that each of the following: A, exactly 10 of them are Democrats; B, at least 10 of them are Democrats; and C, 9 or fewer are Democrats. So I'd like you to pause and try those out, and we'll talk about them in just a moment. Okay, so what is the probability that exactly 10 of them are Democrats? In this situation, n, the number of trials, is 12. Those are the 12 individuals we randomly select. P, the probability of success in a single trial, that's the probability of finding the thing we are looking for. We're looking for exactly 10 of them to be Democrats. So the probability of success in a single trial is 60%, or 0.6. And we're looking for the probability that x is equal to 10. So by our formula, that's 12 choose 10, or 12 factorial over 12 minus 10 factorial times 10 factorial, multiplied by 0.6, the probability of success to the 10th power to the k, times the probability of failure, 1 minus 0.6, so 1 minus 0.6 to the 12 minus 10th power. Simplifying, that's 12 times 11 times 10 times blah, 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 down to 1, divided by 2 factorial times 10 factorial. That's 10 times 9 times blah, 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 down to 1, multiplied by 0.6 to the 10th power times 1 minus 0.6 is 0.4 to the second power, to the 12 minus 10th power, which is 2. Continuing to simplify, we see that sum of the 12 factorial from 10 on down cancels out with the 10 factorial. And so we're left with 12 times 11 over 2 factorial, that's 2 times 1. And so we can further cancel the 12 with the 2 to get 6 times 11, or 66 is what that reduces to, times 0.6 to the 10th power times 0.2 to the second power. And if you simplify that, you will get 0.06385. 0.06385 is our probability. For the probability that at least 10 of them are Democrats, we want the probability that x is greater than or equal to 10. So since there are 12 individuals randomly selected, this is the probability that x is equal to 10, plus the probability that x is equal to 11, plus the probability that x is equal to 12. And 12 is the largest it could be. We've already found the probability that x equals 10. Let's find the other two. The probability that x is equal to 11 is 12 factorial, n factorial, divided by 12 minus 11, n minus k factorial, times k factorial, multiplied by the probability of success, 0.6, to the k to the 11th power, times 0.4, the probability of failure, to the 12 minus 11, the n minus kth, so 12 minus 11 is just first power. So this is 12 12 times 11 times 10 times blah, 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 down to 1, divided by 12 minus 11 is just 1 factorial, which is just 1, times 11 factorial, 11, 10, dot, 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 down to 1. Again, these cancel out, and that's always, factorials always cancel out kind of nicely. You can always pick the larger of the two values, k and n minus k, to cancel out with most of the n factorial. Still multiplied by 0.6 to the 11th power times 0.4. And so simplifying, that will give us 0.0174. This was just 12 times 0.6 to the 11th power times 0.4. And finally, the probability that x is equal to 12 is 12 factorial over 12 minus 12 factorial times 12 factorial times 0.6 to the 12th power times 0.4 to the 12 minus 12th power. So simplifying gives us 12 factorial divided by itself is just 1. This is 0 factorial, and 0 factorial is also defined to be 1. So this is just 1 times 0.6 to the 12th power times 0.4 to the 0th power. Anything to the 0th power is also 1. So this is just 0.6 to the 12th power, which is 0.002. And so finally, the probability that x is greater than or equal to 10 is equal to 0.06385, the probability that x is equal to 10, as we found above, plus the 0.0174, the probability that x is equal to 11, plus 0.002, the probability that x is equal to 12. And if we add those values up, we'll get 0.08325. Now looking at the probability that 9 or fewer are Democrats, so the probability that x is less than or equal to 9. So one way we could do that is do the same thing we were doing, find the probability that x is equal to 0, plus the probability that x is equal to 1, plus dot, 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 the probability that x is equal to 9. But a faster way to do that, especially given what we've already calculated, is to use the complement. So this is 1 minus the probability that x is greater than or equal to 10, because either x is less than or equal to 10, or x is greater than or equal to 10, or x is less than or equal to 9. Those two events are complementary events, since this is a discrete distribution, and we can't have something like 9.2 here. So this is equal to 1 minus the probability we just calculated, 0.08325, and so that's 0.91675 is our probability of that event. All right, suppose 40% of people say that blue is their favorite color. If you have 10 friends and 7 of them say that blue is their favorite color, is this value unusually high? So one thing to note, if we are talking about unusually high or an unusually large value, that's something that happens less than 5% of the time, And when we say an unusually large value, so suppose that like our x is right here, we are interested not just in the probability of x in particular, but the probability that x is that value or larger. Unusually large means that the probability that our value x is greater than or equal to, like so this is k, is less than 0.05, is less than 5%. All right, so is this value unusually large? So we are looking for the probability that x is greater than or equal to 7, which is going to be equal to the probability that x is equal to 7 plus the probability that x is equal to 8 plus the probability that x equals 9 plus the probability that x equals 10. So that is what we're looking for. So finding these individually, the probability that x equals 7, well, our 10 friends is our number of trials. P equals 0.4 is our probability of success. So this is 10 factorial divided by 10 minus 7 factorial, n minus k factorial times k factorial multiplied by the probability of success 0.4 to the kth power, to the 7th power, times 0.6, 1 minus 0.4, to the 10 minus 7, we'll just write that, 10 minus 7th power. And so we could continue to simplify that. That's 10 times 9 times 8 times 7 factorial divided by 10 minus 3 is 3, 10 minus 7 is 3 factorial times 7 factorial multiplied by 0.4 to the 7th power times 0.6 to the 3rd power. And so we could continue to simplify. That's equal to our 3 factorial is 3 times 2 times 1. Our 7 factorial cancels out with the 7 factorial up here. So we could also do some reducing of this fraction in that way. And so we've got 10 times 3 times 4. So that's 120 times 4 to the 0.4 to the 7th times 0.6 to the 3rd. And if we calculate that out, that's equal to 0.0427. So we need to find the probability that x is greater than or equal to 7. So that's doing this calculation out for, again, x equals 7 plus x equals 8 plus x equals 9 plus x equals 10. And instead of going through that for each value of x, again, like we saw above, we would just change for the next one. Everywhere we see a 7, we would put an 8 and so on. But you're welcome to try this out on your own. The total sum is going to be 0.05476. So that is the probability that x is greater than or equal to 7 if we calculate this out. And this is greater than 0.05 or 5%. And so we say that no, this is not unusually large by the definition that we're using in this class. So this is not an unusually large or unusually high value. If 7 of your friends, say that blue is their favorite color, if this was a randomly selected group of individuals, the probability of that occurring is about just over 5%. And so in general, you might say that's a small value, but according to the standard we are using, we are not going to say that that's unusually large value. All right, you're playing a board game and it's advantageous for you if 5 is rolled on the die. It seems like 5 never comes up. Out of frustration, you roll the die 20 times and there's only one 5. Is this enough to say that the die is unfair or weighted? So try that out and we'll talk about it in just a moment. All right, so again, we're looking for the probability that we have x less than or equal to 1, 5. The probability of rolling 1 or fewer 5s in 20 rolls. So n is 20, the number of trials. P is the probability of success, is 1/6. So the probability that x is less than or equal to 1, the probability of a result this extreme or more extreme is the probability that x equals 1 plus the probability that x equals 0. So we have to find each of those. The probability that x is 1 is n factorial divided by 20 minus k, n minus k factorial times k factorial multiplied by the probability of success, 1/6 to the kth power. We just had 1, 5 in this case, times the probability of failure, 5/6, the probability the die is not a 5, to the 20 minus 1, the 19th power. And if we simplify that, 20 factorial divided by 19 factorial, that just leaves us with 20. And in general, n choose 1 is always n, times 1/6 times 5/6 to the 19th power. And if we multiply that out, that gives us 0.1043336. Then we can find the probability that x is equal to 0. So that's 20 factorial over 20 minus k, 20 minus 0 factorial times 0 factorial times 1/6 to the 0 power times 5/6 to the 20th power. And simplifying that gives us 20 factorial over 20 factorial, cancels out. 0 factorial is 1, so this is just 1 times 1/6 to the 0th power is also 1 times 5/6 to the 20th power. And if we calculate that out, we'll get 0.02608. And so these are the two individual probabilities. The probability that x is less than or equal to 1, therefore, is adding those two values together. And so that gives us 0.1304 is the probability of that event. So that happens about 13% of the time. This might be enough to convince your friend that you're playing with that something fishy could be going on here. But again, by the standards of this class, this is greater than 0.05. And so we would say that this is not an unusual event for there to be 1 or fewer 5s out of 20 die throws. All right, so the last problem we'll think about is tossing a coin 100 times. What is the probability of exactly 50 heads? So you could write out the formula for that. Okay, so the probability that x equals 50, we've got n equals 100. The probability of success, probability of a head is 1/2 or 0.5. So the probability of exactly 50 heads is 100 factorial divided by 100 minus 50 factorial times 50 factorial multiplied by 0.5 to the 50th power times 0.5 to the 100 minus 50, also the 50th power. And so you might look at that and say, I could calculate that, but I don't want to, and I wouldn't blame you. So there are different ways you can calculate this electronically. As I said, some calculators contain this. You can use usually the probability button, and then go from there on some calculators. Another option is there's a few different online calculators to help you out. So this first one just calculates n choose k, or n factorial over n minus k factorial times k factorial is this first link. The second link specifically calculates binomial probabilities, and this is what this one looks like. And if you just Google, a binomial probability calculator, you will come up with this or something very similar. So with this one, you can put in your p equals 0.5, probability 1/2 of success in a single trial. Our number of trials, our number of coin flips, n equals 100. You can put in the number of successes you're interested in, n equals 50. And then it will calculate each of the probabilities we're interested in. So the probability of exactly 50 heads in 100 flips is 0.0795, so about an 8% chance. If we look at the cumulative probability, so for example, this is the probability of 50 or fewer heads. So this is the probability that x is less than or equal to 50, so this is 50 or fewer heads. That happens more than half of the time, and so on. So if you're, doing this in real life, you can use the formula, and you can also use a calculator such as this. One thing I'd like to highlight here is that the most likely scenario might not be that likely. So toss a coin 100 times. What is the probability of exactly 50 heads? It's about an 8% chance. So there's an 8% chance of that happening, but it is the most likely outcome out of all possibilities. Like, it's more likely than 49 heads, and it's more likely than 53 heads, and so on. And if we were talking about tossing a coin 1,000 times, what's the probability of 500 heads? That's more like 2% or something. That's, again, getting smaller and smaller to get a very precise value. So the most likely event might not be all that likely if there are many possible different outcomes.